Welcome to the second video for 2.1. We are going to begin finding limits algebraically by using a method called direct substitution. And yes, I know in this first example already I do have a graph. I just wanted to kind of prove the point with a graph. We've already learned how to find limits graphically, and if you can graph something, I highly recommend it either using Desmos online or your graphing calculator, because it really does help to put something visual to a problem that we're trying to figure out. For this first one, we want to find the limit as theta approaches pi over 2 of sine of theta. Now note, theta is just another variable. We use it for angles. It could say x. It doesn't really matter. But we want to know, okay, what is our graph approaching as we approach pi over 2? Well, let's look at it graphically first, then we'll talk about algebraically. If we look at pi over 2, in order for this overall limit to exist, we have to look both from the left and from the right. And it looks like from the left and the right, our y values are approaching the same point, which is 1. So we would say that the limit, well, we could say that it looks like it's 1. In order to prove, we need to use algebra. And so when we use algebra, the first thing we want to do is direct substitution. That means literally plug in the value into our function. So to use direct substitution here, to prove that it is 1, I'm going to say that the limit as theta approaches pi over 2 of the sine of theta is plugging in pi over 2 for theta. So it's the sine of pi over 2. I used direct substitution here. I'm saying when theta approaches pi over 2, I'm just going to plug in pi over 2 and see if it works. A lot of times, the limit is the actual function value as well. All right, so what is the sine of pi over 2? Well, the sine of pi over 2 is 1. We can see that by looking at the graph of sine, or we can look at our unit circle, and at pi over 2, our y value is 1. So the sine is 1. So graphically, we can only estimate what a limit is, but algebraically, we can actually prove what the limit is. Now, direct substitution doesn't always work, but it is our number one defense for finding a limit algebraically. It's always the first thing we want to do is literally just plug it in. We plug it in. If it works, then we're done. Let's look at some other examples for using direct substitution. All right, we have 3 examples here, and these will all work. So if we want to find the limit of this crazy rational function, sure, you can graph this function if you want, but you don't really have to. We can use algebra and just plug in the value of 2 everywhere there's an x. So let's do that. When we plug in 2 up top, we'll have 2 squared plus 6 times 2 plus 9 all over 2 plus 3. And that'll give us 16 plus 9, which is 25, over 5, which is 5. This is a rational function. The domain is all numbers except -3, but we're not dealing with that yucky number of -3. We're dealing with 2. So when x is 2 and all around it, our function's continuous. There's no holes or gaps or anything. And the limit as x approaches 2 is the same as the function value at 2. So our limit is 5. For this next one, we're going to plug in 1/2. So we're going to see if that works. When we plug in 1/2, we'll first square it and then multiply it by 2 to get 1 and then plus 3. So 1/2 squared is 1/4 times 4. That gives us 1. So again here, our limit exists, and we found it very easily using direct substitution, which is an algebraic way to find a limit, by just plugging it in. Let's try the last one. We want to plug in 3 pi over 4 into the function cosine of 2x. So we'll do the cosine of 2 times 3 pi over 4. When we multiply this out, you can either multiply straight across the top, and this is 2 over 1, remember? So 6 pi over 4, or you can cancel the 2 and the 4, which I'm going to do. That's a 1, and this would be a 2. So we're left with the cosine of 3 pi over 2. Using your unit circle, remember that the 3 pi over 2 is down here, and the cosine is the x value down there. That's the coordinate point 0, -1. 0 comma -1, so the cosine value there is 0. It's totally okay to get 0. This is not a 0 in a denominator. So our answer here, the limit, as x approaches 3 pi over 4 of cosine of 2x is 0. Let's look at a couple examples where direct substitution does not work. So let's look at this top example first. The limit as x approaches pi over 2 of this wonderful function here. So I'm going to attempt to use direct substitution as we always should first. So 1 minus the sine of pi over 2 all over the cosine of pi over 2. Remember where pi over 2 is? Pi over 2 is at 90 degrees. It's up top here. And the coordinate point is 0, 1. And remember the sine is our y value. So the sine is 1. So this ends up being 1 minus 1. The cosine at pi over 2, cosine is the x coordinate, which is 0. So we actually are left with 0 over 0. Now, in calculus, actually in math in general, if you get something of the form 0 over 0 or infinity over infinity, which we'll see later, this is actually called indeterminate form. It actually means that the limit still does exist. We just can't find it using direct substitution. We have to go further. And in that case, it might be using trig identities, it might be factoring, it might be rationalizing, it might be sandwich theorem. Like there's a lot of different things that we might be able to do. But when you get indeterminate form, 0 over 0, that means that the limit still exists. We just don't know what it is yet. So at this point, all you can write is indeterminate form. Let's take a look at the orange example down here. Let's plug in 2. When we plug in 2, we'll have 4 plus 6 minus 10 all over 4 minus 4, which gives us 16, gives us 10 minus 10, which is 0 over 0 once again. Again, this is called indeterminate form. I'm not going to rewrite it. But when we have indeterminate form, again, that means that the limit exists. The limit actually exists. We just don't know what it is yet, so we're not quite there. So you can just write indeterminate form at this point if you get 0 over 0. Let's actually take a look at one last example here. Note that this is the same function as this orange problem, except instead of approaching 2, I'm doing x approaches -2. So if we attempt to find this limit using our first line of defense, direct substitution, we will have still a positive 4, but then we'll have a minus 6 minus 10 all over, again, 4 minus 4. When we do this, looks like we'll have negative, 12 up there, over 0. All right, no, this is not indeterminate form. This is actually undefined because we have a non-zero number over 0, and indeterminate form is 0 over 0 or infinity over infinity. But when we have a non-zero number divided by 0, that is undefined. That actually means that no matter what mathematical maneuvering we do, we can't find this limit because the limit does not exist. So please note the difference between 0 over 0. It just means even though we can't find the limit yet, it still exists. We have to do some more mathematical magic. But when it's a non-zero number divided by 0, the limit does not exist. We can't, no matter how much mathematical magic we do, it does not exist. So in conclusion here, what have we learned? When asked to find a limit, algebraically, if you don't have the graph, right, the first thing that you want to do is try direct substitution. Literally means plug in that value into your function. I want to say x value, but sometimes it's not x, but just plug the value in. If it works, like it gives you an answer, yay, you're done. That's your answer. If you get 0 over 0, that means you have indeterminate form. It's called indeterminate form. And even though we don't know how to do it yet, to find the limit still does exist. We just need more learning. All right, and let's say you get a non-zero number over 0. That means the limit does not exist, because this means undefined, whereas this is indeterminate form.